Okay, so the easiest problem of the contest was problem A. We were given a string of A's and B's. The length of the string was less than 10 to the fifth. And the only operation we were able to do is to take the first and the last occurrence of one symbol, for example, the first and the last occurrence of B, and just delete them. If there were more B's, we could have taken those two B's and deleted them as well. Also, we can take the first and the last occurrence of A and delete them as well. And we were able to do as much operations as we could in order to obtain lexicographically smallest sequence possible. So this was the easiest problem, and just a simple case analysis was enough to solve this problem. So the first case is the number of A's equals 0. Then the only thing we have is just B's, and the answer is either B or BB. It depends on the parity of the number of B's. We just delete all of the B's, because like if you have a sequence B, 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 we can delete the first and the last one, and the sequence with two B's is lexicographically smaller than the sequence of 4 B's. So if number of A's is 0, we just have B or BB, depending on the parity. The next case is the parity of number of B's is 0. So we can write it like number of B's modulo 2 equals 0. In this case, we delete all the B's, and what we have is just an A or AA, also depending on the parity of A. So the same logic as here applies. If we can delete the pair of A, we just do it and obtain a lexicographically smaller number. And in this case, it is always good for us to delete all the B's. And the last case is number of B's modulo 2 is equal to 1. In this case, we are going to be left with 1B if we delete. Well, in this case, it is always good for us to delete all the B's except 1. So this will be, let's write an example, A, B, B, A, B, something like this. In this case, number of B's is odd. And if you're trying to obtain the lexicographically smallest string, we just try and delete all the B's, and we are left with the one that is in the middle. We cannot do anything about this B, and there are two cases left. One case is the string starts with B, and then there is a bunch of A's. In this case, we want to delete as much of this A's as possible using this logic, and we are left with just a B or B8. And the other case is that B is not the first letter, but we have B, then here we have a bunch of A's, and here we have a bunch of A's. And we just leave it like that because we want as much A's as possible before the B in order to have the lexicographically smallest possible string. So those cases are actually really easy to analyze, and I'm sure that almost everybody solved this problem. If there's no question, we're going to go to the next problem. So that was problem A. And the next one, I believe, is problem G. Can you do this? You were given two integers, A that was less than B, and we had to find out the smallest possible integer C, such that A or C, this is a bitwise OR operator, would be larger than B or C. So we have to like swap the values of A's and B's while ORed with C. Yeah, or we had to say that such number doesn't exist. In order to solve this problem, the first thing we have to do is to convert A and B's to binary. So we will have something like 0, 0, 1, 1, 0, 0. That's B. And A has to be smaller than B. It's like 0, 0, 1, 0. 0, 0, 1, 1, 0, something like that. And then we just go from left to right and look at the bits. We go from the larger bits to smaller bits. If you have 2 zeros, we just skip them. 2 zeros, we just skip them. 1, we just skip them. And here we have in B bit 1 and in A bit 0. If you want A to be, if you want A or C to be not to be less than B or C, then we have to set this bit to 1. We have to set this bit to 1. So this bit has to be set to 1 in C. Here we construct a C number. Then you just continue. We have a couple of zeros, we just skip them. We have 1 and 0. We set this bit in C to 0, to 1. And then we have 1 in A and 0 in B. At this moment, we can just stop the process, fill the rest of the bits in C with zeros, and we will know that this condition would apply because this prefix was constructed in order for A to be not smaller than B. And in this bit, we have that A has 1 and B has 0, which means that this number would be greater than this number because the prefixes are the same, and in this bit, A is larger than B. Okay, so we just go from left to right. If you have 2 zeros, we skip them. If you have 2 ones, we skip them. If you have 1 in B and 0 in A, we set this bit in C to 1. And if you have 0 in B and 1 in A, we just stop the process and return the value of A that we computed so far. So that was also an easy problem. The complexity was of logarithm of A maximum of A and B, something like this. It was also quite easy. I believe almost each team managed to solve this. Any questions? Okay. That was problem G. And the next one, Vitaly will tell you about problem I. Yes.
Okay, so in problem I, you were given a tree, and you had to remove some number of edges from it in such a way that all the remaining connected components are stars. So a star is a component that has a single vertex that can have a degree larger than 1, and all the remaining have to have the degree 1. So this is an example of a star. This is also an example of a star. This is also an example of a star. And this is also an example of a star. Okay? But this is not. That's not a star. Because you have 2 vertices with degree larger than 1. Okay. So you have to remove some of the edges in such a way that all the components are stars, and you are allowed to remove less than n divided by 2 edges. Yeah, if you consider it like this, then yes, let's go. Yeah, well, yes, like this. Okay, so here's how you can do it. If you select any vertex, and you can say that this is now a root of your tree. Then you can run a DFS algorithm from this vertex, and you can visit all the remaining vertices from this. And in this way, all of the vertices will have some height. So the distance from the root, right? This is 0, this is 1, 2, 3, and 4. Okay. Yeah. So what you can do is you can, for example, remove all the edges from every other height. Okay. So we can remove all the edges here, all the edges here, and if you had one here, then here as well. So you will remove all the edges from every other level. Okay. In this way, obviously you would only have stars, right? Because you would only have edges that are on the same level, so they can only do stars, nothing else. And there could be a case that the number of edges on this level is larger than n divided by 2, in which case you can just remove all the other edges, right? Because there are, so in total, there are n-1 edges, right? So if this set of edges is larger than n divided by 2, then all the other edges will be less than n divided by 2. So if this is not okay for you, we can leave all of these edges and remove all of these edges, which I believe is the solution for this particular case. Yeah, that's it. Any questions? No. Let's move on.
That was problem I, right?
Yes.
Okay. The next problem is problem F. Problem F was a simple constructed problem. We had a bunch of segments, a segment with size 1, segment with size 2, 3, 4, and so on, and -1, and what we have to do, we have to arrange them in a line so that any 3 consecutive segments, we cannot make a triangle from any 3 consecutive segments. Okay? For example, if we look at the sample had n equals 4, and the answer was 4, 1, 2, 3. There are 2 possible triplets of consecutive segments, 4, 1, 2, and 1, 2, 3. And neither of them constructs a triangle because 4 is larger than 1 plus 2, and 3 is larger than or equal than 1 plus 2. Okay, so basically the solution for this problem is just a simple pattern that you could have come up just by the brute force algorithm, or just writing bunch of ways to put them on a paper, and the pattern is the following. Let's first imagine that n equals 3k, n is divisible by 3. Then we do the following: 1, k plus 1, 2k plus 1, then 2, k plus 2, 2k plus 2, and so on. And we finish with k, 2k, 3k. A pattern like this. It works in every position, so it works here, 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 and so on. You can check it on the paper. It works in each position except one that is right here, and the number that is here should be 3, k minus 1. the only place where the pattern doesn't work is this pivot, I believe. Is it the case? It is the case because 3k minus 1 is less than k plus 2k. And we can construct a triangle from those three numbers. And what we do, we put 3k in the place of 3k minus 1, and 3k minus 1 we put at the beginning. So the actual pattern looks like this. It starts with 3k minus 1. Then we have 1k plus 1 to k plus 1 and so on. Here we have 3k. And we finish with 2k. I will just double check if I made a mistake. Yeah, this, I believe this should be a correct pattern. Yeah, you can check it on the paper if it works, but I believe it should work. So that's the solution for n that is divisible by 3. And now if n equals 3k plus 1, we put this 3k plus 1 at the beginning. And if n equals 3k plus 2, we put this 3k plus 2 at the end. And both of those cases should work fine as well. Yeah, so that's basically the solution for this problem. You can come up with this pattern by some brute force algorithms or just by trying different ways to put them. Okay, any questions? Let's move on. That was problem. The next one is problem C, 0 cycle. In this problem, we had oriented graph. And yeah, the number of vertices was up to 10 to the 5th. Number of edges was up to 2 times 10 to the 5th. And it was guaranteed that there are no loops. So, and like this was not possible. And what we had to do is to assign weights to all the edges. Weights should have been in range from -1000 to +1000, except 0. So the weight of edges could not have been 0. And the condition was that on each cycle, the sum of the weights of edges should be equal to 0. Okay, so that was the statement. We had to assign weights to edges from this range so that there are no zeros, and the sum on each cycle is equal to 0. And we had just to output them. And the solution for this problem is the following. First, let's forget about the orientation of the edges and imagine this graph as like a graph with edges that are go both ways. So just a simple graph. Something like this. And now let's color this graph into 1,000 colors. And here the common rules of coloring of the graph applies. If two vertices are connected by an edge, they cannot have the same color. So imagine that we know how to color this graph into 1,000 colors. Now having this coloring, let's discuss how to get a solution for the problem, how to get the weight of the edges. Let's write here some colors. 1, 2. Yes, we are coloring vertices. of the graph. Yeah, and I'll draw the directions. Yes, we have something like this. Those are the colors of the vertices. And now, if you have an edge from vertex with color X to a vertex with color Y, let's assign weight X minus Y to this edge. So in this case, the weight would be -1. In this case, we go from 2 to 1. The weight is 1. In this case, we go from 1 to 3, and the weight is -2. In this case, from 3 to 4, the weight is -1. From 4 to 1, the weight is 3. From 2 to 3, the weight is -1. 3 to 1 is 2. 1 to 2 is -1. And from 2 to 1, it is +1. I will circle the weights of edges. Okay, so if we assign weights in this way, first, there are going to be no edges with 0 weight, because we have a valid coloring of a graph, and no two vertices that are connected with an edge have the same color. So that's the first condition, we will not have zeros. And the next condition is for each cycle, we have a zero sum of weights of edges. Let's start in one particular vertex and go through some cycle. If you go from this vertex to this one, then the sum is, oh, basically, if we start at the vertex and go to the cycle, then we basically, if we go from 1 to 2, if we, okay, let's start at some vertex and we have a color of this vertex 1. And let's calculate the following. Let's go from this vertex to this vertex, and we go through an edge with weight -1, and let's subtract this -1. And we have to, like, we're going through some cycle, and we are, each time we go through an edge, we subtract the value of an edge from our current number. If you go from this vertex to this vertex, we have 2. If you go from this vertex to this vertex, we have 2 minus 1, and we obtain 1. Then you go from this vertex to this vertex, we have 1 minus -2, that's the weight of this edge, and we obtain 3, and so on. So each time we go to the next vertex, if we subtract the weight of this edge from the color of the vertex, we obtain the color of the next vertex on this cycle. And if you go through the whole cycle, we end up in the vertex we started with the same color that it was at the beginning. And if we add up all of these numbers that we were subtracting, we will receive just a 0. The sum of it would be 0, which is a sum on the cycle. And that basically proves that on each cycle, the sum would be just a 0. Because each time we go from one vertex to another, the weight of the edge just changes from the color of the first vertex to the color of the second vertex. And if you go the whole cycle, we end up in the vertex that we started with the same color. So the sum on this cycle is equal to 0. That basically have to prove that this solution is correct. Any questions about this part of the solution? Okay, so the next part of the solution is to actually obtain a coloring into 1,000 colors of a graph with 10 to the 5th vertices.
And
yes.
And number of edges also.
Yeah, the number of edges is up to 2 times 10 to the 5th.
There are some questions in comments.
Yes.
Why is 0?
Sorry?
Why is 0?
Why is 0?
So, some.
Let's consider some paths in the graph. Each vertex has its color. That we assign a color to each vertex. So C1, C2, C3, C4, and C5. Then we assign weight to the edges. The weight of this edge is C1 minus C2. The weight of this edge is C2 minus C3. The weight of this edge is C3 minus C4, and the weight of this edge is C4 minus C5. Now let's calculate the sum of the weights of the edges on some paths. So for this path, it would be just the sum of those numbers. And we can see that C2 is going to cancel out, C3 is going to cancel out, C4 is going to cancel out, and the only thing we are left with is C1 and C5. So the total sum of weights of the edges on this path is C1 minus C5. It is a difference between the color of the first vertex and the last vertex. Okay? Now, if we have a cycle, so if we have edge like this, and we go a whole cycle, so we sum up the weight of edges on the cycle, then we end up with value C1 minus C1, because we start and end in C1. And this is basically 0. I hope this answers the questions about 0. Okay, any other questions? So basically, if we sum the weights of edges on some simple paths that are constructed in this way, then the result is just the difference between colors of the first and the last vertex. And if you have a cycle, then this difference is 0. Okay. Now about the coloring. So we have a graph with n up to 10 to the 5th edges and n up to 2 times 10 to the 5th. Then 10 to the 5th vertices and 2 times 10 to the 5th edges. And we have to color the vertices into 1,000 colors. So let's divide all of the vertices into 2 categories. The first one are the vertices such that degree of vertex is larger than square root of 2 times 10 to the 5th. The degree of a vertex is a number of edges connected to this vertex. And the second one are the rest, the ones that have degree of this vertex less than square root of 2 times 10 to the 5th. And for each vertex from this category, well, for the first category, we know that there are less than square root of 2 times 10 to the 5th vertices of the first category. Because basically each of them takes up this amount of edges. And if you have more than this number of vertices of such kind, then we end up with more edges that we can have.
Probably four times that.
Yeah, maybe each number we have to have like 2 times or something. Well, this doesn't change the idea. So the number of these vertices is not very large. And for each vertex from this category, we assign its own unique label. The labels that are going to go to this category is 1, 2, 3, 4, and so on, the number of these vertices. That's the first step. We just assign unique colors to the vertices from the first category. And then for each vertex of the second category, we know that the degree of this vertex is less than 2 times 10 to the 5th, square root of 2 times 10 to the 5th, which is less than 1,000. And now let's just go through those vertices in some order and look at a vertex. And let's go through the neighbors of these vertices that have already colors assigned to it. And let's say that all of those vertices combined, they produce a set S of colors. So those are the vertices that are neighbors to our current vertex that are already colored, and the colors form a set S. And the color of this vertex cannot be a color from this set S. And let's just assign the following color. That would be the function max of S. Max is a minimal exclusive number. So if there is no 0 in this set, then we assign just 0. If there is no 1, we assign 1. If there is no 2, we assign 2. So we basically just find the smallest integer that is not in this set, and we assign it the color of this vertex. We know that the degree of this vertex is less than 1,000, so the number of elements in set S is less than 1,000, and this number is less than 1,000 as well, because well, if there is like, all of the numbers, if there is 999 numbers in this set S, numbers from 0 to 999, then we just assign 1,000 as well.
Якщо ми не знаємо колір якогось сина, то ми просто його опускаємо.
Yeah, we just ignore him.
Тобто спочатку ми замальовуємо ті, що з першої категорії, а потім поступово.
Exactly. We first assign those larger vertices, and then we go through the second type in any order. You just color them. So for each vertex, we look at the neighbors that are already colored and take the minimal excluded number from the set of colors. And that's basically the solution.
А Макс шукати просто перебором від 1 до 1000. Не буде 1000, наверное.
Заходить. Any other questions? Any questions from the internet?
But we can't have colors.
Why 0?
Sorry.
Why not 0?
Okay, let's go on. The problem E. Problem E was geometry problems. Everyone's favorite. We had a bunch of vectors. Up to 2 times 10 to the 5th. And we had to select a subset of those vectors. For example, this one, and this one. After that, we compute a sum of those 3 of those vectors that we selected. And our task was to maximize the length of this sum. So we have to find the subset that maximizes the length of the sum of this subset. And we had to output the third length of it. Okay, so the solution for this problem is based on two statements. The first one is the following. If we add,
А ми можемо взяти скільки хочемо векторів.
yes, we can take as many vectors as we can. We can take all of them. Also, we can take none of them if we want to. But I don't think we would want to take none of them. So the first statement is if we have two vectors that we add to an answer, these are vectors A and B, and there is a third vector C that lies in the angle between those first two that we take to the answer, then it is always good for us to take C to the answer as well. Okay? So basically, if we take two vectors to the answer, then we take all of the vectors that are between those two as well. What this means is that if we sort all of the vectors from the input by the angle, then the vector that we take to an answer is going to be like some consecutive segment of those vectors. So we don't skip them. We just take all of them in some consecutive segments. That's the first statement. And the second statement is if we have two vectors A and B, and the resulting sum vector C, and three of these vectors are not lying in one half plane, then one of A and B should not be taken to the answer. Okay?
C is the current sum.
Excuse me?
C is the current sum.
Yes, C is the current sum. Not the sum of A and B, but the sum of
Sum vector.
of vectors that we take. So in this case, either A or B or both of them should not be taken to the answer. But in this case, this is A, B, and C, and this condition does not apply because all of them lie in the same half plane. That's the second statement. And basically, this second statement means that if we draw a line through the origin, then for this line, we should take either all of the vectors on the one half plane or all of the vectors on the other half plane. So either this half or that half. And from now on, the solution basically is we just rotate this line, go through all the possible combinations, and for each angle, we just compute the sum on the left and the sum on the right. And for each such option, we just look at the sum and we take the longest one. So basically, the solution is some sort of a two-pointer algorithm with some geometry, not very hard. We just go through all of the possible options of a half plane that the vectors are in and just maintain the sum of those vectors. And that's basically the solution. Some very easy geometry should be applied in order to solve this problem. Any questions? Okay, now let's move on to the three of the hardest problems, which are going to be complementary.
There's a question.
Yes.
Why all on one half?
Sorry.
Why all on one half?
Why all not 1/2? Because of the second condition. If we, in order for this situation to happen, we have to take to the answer some vectors that go in this direction. So one of those vectors should be taken in order for the answer to be in order for sum to be going in such a way that we cannot draw one half plane for all of the three of these vectors. And basically, if we take just one half plane vector from one half plane, then this situation will never ever happen, because all of them look in this direction, and the answer is also going to be looking in that direction as well. And if we take a vector from this half plane, then we will have exactly this situation, because we have this vector, we have a vector sum that goes somewhere here, and we have this vector, and three of those are not looking in the same half plane. That's basically the second condition, and the answer is not optimal. One of the vectors should be removed, either this one or this one. I'm not sure if you can see anything in this picture, but if it is still not clear, then I'll try to explain it in the other way, and otherwise we'll just move on.
Будет ли больше вектор, если мы не возьмем один из векторов из одной половины?
Да.
Будет ли больше вектор, если мы не возьмем один из векторов из одной половины?
No, because of the first condition. If we take two vectors, then we have to take a vector from between those two. So we draw the picture once more, then what we have to take is just some segment of consecutive vectors. So we cannot, if we skip one of them, then the answer is not going to be optimal because of the first statement. So we are not skipping vectors.
Another question. What if we have two vectors?
What do you have vectors? Or and
Or 2 and minus.
or minus or 2. Then
Why can solution like take more vectors and thus make its own worst?
yeah, the value before 2 if we consider a half plane like this. So we just take this line and we rotate it all the way to 60 degrees, and we try all possible combinations. And when the line is going to be in this angle, then we consider this half plane, and the only vector in this half plane is this vector, which is the answer. So we try all the possible combinations of a half plane, and we maximize the result over all possible angles of this half plane. Should we move on?
I'll wait. let's now move on to the problem D. This problem was actually solved by one team, at least that's as far as we know. And so here's the statement. So you had a sequence of integers 8, and you were randomly shuffling the sequence, and you had this sort of a routine or algorithm that was going through the elements from left to right and counting all the GCDs of all of the subsequent elements. So we had basically for a randomly permutated initial sequence, you will count how far can you go from left to the right, such that you end up with GCD equal 1. And your task was to compute the expectation of this number of steps that you would take. As this problem was solved by one team, I'll just encourage them to come up and explain it, whoever solved it. So go ahead.
Okay.
In English, please.
Okay. So in short, answer will be equal to sum.
Some?
Yes. Answer will be equal to sum over m from 2 to n. This is function of values multiplied by sum over I from 1 to, oh, okay. Let's do some, let's introduce some variables. Let C of m be equal to the number from this array which are divisible by m. For example, if array is equal to 4, 7, 4, 13, then m of C of 2 will be equal to 3 because there are 3 numbers divisible by 2. This 3. And C of 7 will be equal to 2 as only 7 and 14 is divisible by 7. Okay.
Ще раз можна визначити такі C?
Кількість чисел, на які діляться. Зараз. Це від m, це скільки чисел з масиву діляться на m. Тобто, типу, десятимірки 7 і 14 ділиться на 7, двійки там 4, 4 і 4. Окей. Sum over I from 1 to C of m. Product over J from 1 to I. C of m minus J.
А Z це типу сума?
Ще раз. Сигма це сума, P це добре. Divided by n minus J plus. Something like that. Okay. Why this is true? Let's introduce more variables. First, let f of I will be equal to the number of subsets of the initial array whose GCD is equal to 1. So it is number of some x1 is less than x2, so less than and such that GCD of ax1, ax2, and so on is equal to 1. How to calculate this thing? We don't know how to calculate this thing, but we can calculate the complement. So let's calculate f something I, which is equal to the number of subsets whose GCD is not equal to 0, or is not equal to 1. And then we will have that f of I will be equal to f of I will be equal to number of possible sets of all will be A of n of I. So it's basically n factorial divided by n minus I factorial. Right? Something like that. And how to calculate this? We can do this by applying and when we need to calculate this, here it is where Möbius function 10 to the. So I claim that this is equal to sum over m from 2 to the n is, we will say that n is 10 to the 6. And we will use this. Okay, sum over m from 2 to n, mu of m multiplied by what? By some coefficient. By, I believe, n factorial. Типу n factorial буде що? Це n. C of n divided by C of n factorial minus something like that. And here we must have we have C of m numbers which are divisible by m, and we need basically one term of this sum. Let's consider, for example, m equal to 2. We want to add up to calculate the sum of such numbers that GCD is divisible by 2. How many such numbers there are? We can like something like this. Because, for example, if m is equal to 2 and I is equal to 2, we can choose either 4 and a 4, 4 and 14, or 4 and this 4 and this 14. Like number of choosing of some I elements out of C of m elements. So, and it is known that it should be calculated with some formula which should look like this because of inclusion-exclusion. So I believe after we plug this to this equation, we will have one more long equation. And how to calculate this? We will also notice some facts about the original sequence. At first, I don't know whether it was necessary, but let's remove all, let's make all prime powers of numbers from initial array to be 1. What I mean is, like, if we have numbers 2 to the power 3 multiplied by 3 to the power of 2 multiplied by 5 in the array, which is equal to some number. Let's just erase this number from array and put instead 2 times 3 times 5. No, it is easy to see that this doesn't change anything. But now we can notice the fact that 2 times 3 times 5 times 7 times 8, 11 times 15 times 17 times 19 is bigger than 10 to the 6. That's why there are no more than 128 divisors of any number from the initial array at all. So each element from the initial array A has no more than 138 divisors. After the process we described at first step. And now we will say that the following sum over m from 2 to n c of m is not bigger than n times 128, which is something like 10 to the 8. And our algorithm will work at that complexity. Why? Because we can calculate, like, go for each m from 2 to the n to n, and then from I from 1 to the c of m, and keeping this product, like when we go for this product, we can say that it is equal to something like and so on, 1 divided by n minus cm plus 1. And sum over, like, okay, sum over e from 1 to t. And we can calculate this product in not c, like, if we do this straightforwardly, we will have the complexity c of m squared, like this complexity, but this is bad. But we can easily improve this by keeping some. It's easy, but easy if you manage to understand this.
Shouldn't this product be multiplied by I
M minus 1.
under this sum?
This is an expectation.
The product.
Yeah, this product.
Yeah. Shouldn't it be multiplied by I?
When we wrote our equations, this I will be cancel out, because we will have something like, we can't directly imply this to this formula, because we need to cancel out, like, f of I is number of subsets whose GCD is equal to 1. But we need our answer at initial formulation should be n equal to sum over I from 1 to n, I multiplied by not f of I, but f of I minus something like f of I minus 1 multiplied by some other coefficient, and they will cancel out. Because we need not only that f of I, GCD of i's element will be equal to 1, but also that GCD of the first I minus 1 elements will be not equal to 1. So it will be f of I minus f of I minus 1 multiplied by some other coefficient like n minus I plus 1 or something like that. But you need to be very careful with this. And we struggle a lot to make this formula work. Okay. Maybe some questions? I don't know why this works fast, but because the operations are quite.
Just one suggestion or question. So when you're calculating this CM, how exactly did you do that?
Oh, okay. Okay, if you do this straightforwardly, okay, there are two ways of doing this. At first, we can generate a series of errors, and then for each number of array, we can write out all its prime divisors, like P1, P, and so on, P7. There will be no more than 7 of them. and just for each bit masks of this, like calculates each mask of 7 elements and do some stuff, but it will be too slow. So you need to recalculate some other stuff, like for each.
Sorry, did you try that?
Yeah, we tried it and it works like 3 seconds locally. And
So you iterated over all masks.
yes, for each number from 1 to 6, I write out all of the divisors, prime divisors, and then iterate over each mask, and then take a product of these numbers and like increase some sum.
Yes.
But this will be too slow because there is possible max test where which we have. It was like all the numbers are equal to this number, and the last one is 1. And on this test, this will be too slow, but you can use some hacks to improve this.
So that's what you did, some hack.
Yeah. Like,
does anyone know a better solution to this?
How to find all CMs.
Sorry?
The question is how to find all CMs.
Yeah. In a better way than this.
in better ways than just generating all masks and writing them. Probably it can be done easier.
So I think that you can just do the following. So if you know that all this. So no.
7 elements. Why can
We can work. Okay. Wait, 1 second. So if you have di, so di is the how many times I was in the input. Okay. How many times I occurred in the input?
Oh yeah, I understood.
That's it.
No.
Okay. So you can just, if you have this di, then you can just add this di to the like I plus I, e I plus, so 3i and so on.
No, I mean
Why not?
for each number of input you need to all its divisors, not multiples. Типу, сейчас таки делятся на які одинаками і вони діляться на них. Типу, не і двої, три.
Yes, you can add all of these numbers here, all of these numbers here, and so on.
Okay.
So basically, the I equals to the sum of those numbers.
Okay, that was the first idea, and it was even worse by time.
Isn't this n log n?
Yes, it is n log n of backs in that, or
What?
of many number back in back. What?
This is just an array of integers. So you just count the number. So basically, if you have the so di is the number of times I occurred in the input, the 2i is the number of times 2i occurred, and so on. So this means that ci will be equal to di plus d2i plus d3i, and so on.
Okay.
So that's just n log n.
Yeah. That's very easy.
No need to have any masks or this.
Okay. There was question why there are no more than 7 prime divisors, because as I wrote here, if you multiply 2 by 3 by 5 by 7 by 11, like 8 the least primes, you get a number which is far bigger than 10 to the 6.
Yes.
So each number can have only up to 7 prime divisors. That's why complexity will be n multiplied by 100.
Можете ще раз пояснити, як CM шоти?
От ось ти маєш
CM – це кількість чисел А, що діляться на n.
кількість чисел з початкового масиву, які діляться на n.
Ну, саме очевидно, це взяти кожний розбір на дільники і
Ну так, це те, що я казав, це було розглядаємо для кожного числа, розглядаємо його прості дільники, шукаємо там, прибираємо його маску.
а що важко.
Ну так швидше, ніж до за корінь ітеруватися. Ну так, найпростіше це було просто за корінь проітеруватися і це. Але так би було занадто довго. От, тому типу можна порахувати. Тобто у нас є якийсь масив А початковий, порахуємо масив С, ну добре, масив Д великий, такий, що, ну там, Д маленький, дуже. Такий, що де іти це скільки раз число І зустрічається в масиві. Скільки раз число І зустрічається в масиві. І тоді це іти, це буде Д іти, плюс Д2 іти, плюс Д3 іти і так далі. Ну так, це набагато легше, ніж те, що я говорив сам. Це є.
Щось повторяємо по цих числах, які діляться на І.
Ну і тут, типу, коефіцієнти мають бути якісь приблизно такі. Тобто там вони не запутались.
So yeah, and this will have a complexity of n log n.
Yeah. But do you know how to do the second part, which is better complexity than n multiplied by 128?
There is actually a different solution with a better complexity, but it runs slower than this solution. So yeah, you can do it like that.
Any more questions?
Okay. So now we have two more problems. So the first team actually tried both of them. Maybe they solved all of them. We don't know. Oh yeah. That was D.
Я зараз це записав, мені здається, я нічого не розумію, точно. Тоді писали,
Okay, so let's start with problem B. So in this problem, you had to count the number of ways you can put towers in such a way that this combination is lucky. So what this means is that if you have some towers, they all have some height, okay? And for each tower, you would calculate how many other towers you can see from this particular one. And you can see another tower from the current one if there are no higher towers in between them, higher than the one that you're looking for. So, for example, from the first tower, you would see the second one, the third one, and probably this one. Okay? You won't see any of this because you have a larger tower here. And if you had a sequence A, which are the heights of the towers, then you had to find, for each such array of heights, you can calculate V, which is the number of towers that you see from each of those. You have to calculate how many such combinations of heights are that A equals B. Okay, so how we can do this? So you have to do a couple of observations first, and then we'll build a dynamic programming solution on top of those. So, what are the observations? So it is a good idea to focus on the highest tower that we have in our sequence. So let's assume that we have just one of those. So there is one tower that has the highest. That is the highest. Okay? Yeah. So all of the towers that are to the left of it are smaller, and all of the towers that are to the right of it are also smaller. Okay. So what you can actually see from this is that in some way, those two sequences to the left of it and to the right of it become in some way independent. Here's why. Well, we need what conditions do we have to meet in order for this to be a valid sequence? So we need to see. So if this is k, for example, so the height of this is k, right? So we need to see some number of towers from this one. Let's say that those are the towers that we see from the. Oh, sorry, I'll be larger than this one. Let's say that we see 4 towers on this side and 2 on this. So in this case, we can say that k should be equal to what? 2 plus 4 is 6. Okay. So basically, we can say that if we have the largest number here, then we'll call this a stack size, which is basically the number of towers that you can see from one side. So this stack size of the left part plus the stack size of the right part should be exactly the height of the tower. Okay. Yes. So that's the first observation. And yeah, if you can actually calculate the number of valid sequences that you have on the left side that have this number of some number of some stack size on the left and some stack size on the right, and the sum of those is equal to your largest, and also that each of them is smaller than our largest one, then you can calculate the output. This can actually, from this you can actually follow to some dynamic programming solution, but since our constraint is 1,000, most probably this won't work, just because it should be too slow. But you can actually derive some solution from just this observation. Okay, we need to have a little more observation to simplify our solution. Let's say that we'll have to prove some statement. So let's say that we have the largest tower of size k, just like we said before, and let's calculate what is the stack size of this whole sequence if you look from left, and the whole sequence if you look from right. So the statement is that this left, so the stack size that we see from the left, will be equal to the stack size from the right, and it will be equal to k divided by 2 plus 1. So that's the statement that we have. So this is actually a pretty powerful statement for us, because now we would know that if we build this sequence, that if we have the largest one, then the stack size from the left will be equal to the stack size from the right. Okay. So let's try to prove this, and maybe on the way there we will actually see how the solution should look like. Okay, so yeah, let's say that we have this tower is of a even size. Let's say that let's forget about this, and let's say that our tower has size 2k, so it's an even size. Okay. So we need to prove the statement that we just had, that L equals R and equals to, well, let's call it M, which is basically M equals to K. This divided by 2 plus 1. Okay. So we need to prove this, and we can do this by basically recurrently. So let's say that we have proven this for smaller sizes of the sequences, and we need to prove this for the whole sequence. And assume for now that the largest one has an even size. Okay, so if you prove this for smaller, then what we should see on the left and what we should see on the right should have a height of, well, on the left it should be 2k minus 2. And on the right, it also has to be 2k minus 2. Well, why is that? If you have something here that has a height 2k minus 2, this means that the left and right stack size will be basically k minus 1, right? And on the right as well. And we no, actually it will be yeah. So 2k minus 2 divided by 2 plus 1. So that's k. Yeah. So on both sides we will have k. This means that this tower will see k on the left and k on the right as well, which is the correct thing, we hope, because we need it to see 2k of those. Okay, so, well, basically what it means is that we can reduce our problem to the same problem on the left and on the right of the highest tower. And we need to have the height of this left part. By the height of the left part, I mean the height of the highest tower on the left part, to be equal to k minus 1. And we need to have the same thing on the right part. Okay. Well, why you cannot have any smaller size here? Well, you can see that if you have 2k here, then you need to have at most 2k minus 2 here. So each time you subtract 2 of your height, so you won't have a depth larger than k. And you need to have 2k as the sum of both sides. So you actually need to have a height 2k minus 1 on both sides. Okay. Yeah. You can prove the same thing for 2k plus 1 in a similar way. But in this situation, you would actually need to have at least 2 of those maximums for this condition to be applied. If you don't have 2 maximums, so basically 2 towers of the maximum height, you won't be able to achieve 2k plus 1. If you have 2 maximums, that actually each of them can see each other, that's this plus 1 that we need to achieve. Okay. So what this means for us is that, well, in general, this was the case when we had just one maximum. Let's say that we are building a sequence. We are actually putting some number of those maximums in our sequence. Well, let's say that we have 2 parameters. We have n, which is the size of the number of towers that we are putting, and we have some m, which is the height of the highest tower. Yeah. So again, let's say that we have this situation. The other one is you can look at the other one in a similar way. We have a situation where the height is even. So we have a tower 2k here, 2k here, 2k here, 2k here. So as we said before, you need to have a tower of height 2k minus 2 here. There's just no other way for you. And you need to have 2k minus 2 here as well. What you can have here, you actually have two choices. You can have a tower of height 2k minus 3 or 2k minus 4. Why is that? Because each of those towers here will see both of the heights between them. All of those that are here will just see one. So we have two choices here, and you actually have to have those one of those in the middle. The same for this and for this. Why those two? Because as we said here, we have this equation which was proven before. We actually have, of course, it's of course rounded down, and either of those would end up with the stack size as we need. Okay. So what you can see from this is that if you put some number of those maximum values, then you need to have similar solutions with the with this stack size smaller 6 by 2 between them and on the sides. Okay, so from this you can actually see that the height that we have won't exceed logarithm. Just because this would, otherwise this would just grow too much. Because if you put at least one of those 2k's, then we have to have solution for 2k minus 1 and 2k minus 2 on either side, on both sides. Okay. So this actually proves that the height of the towers won't exceed logarithm. So this will be smaller than yeah. Okay. So with this, you can actually try to do some dynamic programming of putting. So you have this state, right? You have the number of towers that you have to place and the size of it, and you can use all of these observations to put maximums at some positions. So to make this well, basically on top of this, you can already build some dynamic programming. And well, just to make it run fast, you need to have some additional states here that would remember what choice of those you had and what is your current state. So you would just need to place just one maximum from the left, and then maybe put some other maximums after that. So you cannot put all of them in a single transition of your dynamic programming, because that would be slow. We have to put those one by one. Yeah. So I guess you will have to figure this out on your own, because it was really hard to explain all of this on the Blackboard. But you have to use this observation of how can you put those heights. The same thing goes for k plus 1. And you need to handle all of, well, both cases separately. Again, the main observation is this, that this actually means that when we place the highest tower, we actually divide our problem to two smaller problems with the height smaller by 2. Yeah, well, at least in this case. Yeah. Any questions? Oh, okay. All right. If there are no questions yet, we have one more problem. Problem H. So in this problem, yes, so you had some number of balls placed on a line, basically, on some cells on the line. They're placed at some positions initially. You're giving those positions, and there were no more than 2,000 balls. And you also had number n of pairs of integers xy and yi, and you could for each of those you could decide the direction. So each pair could lead to a robot that can go from xi to yi, or the other way around, from yi to xi. So what do we mean by this robot? So what a single robot can do, if he goes from some cell xi to some other cell yi, he would just push all of the balls on the way. So, and yeah, so basically for this picture, it will go from here to yi and push those two balls here. So they will now be placed here and here. Pretty much like that. Yeah. So your goal was to be able to use your robots in such a way that you can put all of the balls in a row without any empty space between them. And well, you should know that no two balls can occupy the same cell. So at any moment of time. Okay. So you have to decide the direction for each pair to have those either robots that go from this side or to this side, and then you can use those robots to achieve your goal, which is to place all the balls in a consecutive row. And you can use any robot any number of times in any order. Okay. Yes. So the first observation here is, well, let's assume that we already assigned a direction for each pair of integers that we have. So we already have basically all the robots that we have. In this case, we can say that we can actually look at the leftmost and the rightmost balls that were initially placed and forget about any of the balls in between. Here's why that's true, because if we put the leftmost ball and rightmost ball as close as possible, so if the position of this one is L and the position of this one is right, then if we can push the leftmost ball as far to the right, or the rightmost ball as far to the left, then all the balls between them will be also placed in a row. So you can just forget about all the balls in between. Just focus on the leftmost and the rightmost. Okay. So now, what we can do from here is that we can actually achieve a greedy algorithm from this, given that we have the initial directions. We want to place the leftmost ball as right as possible, and vice versa for the rightmost. How we can do that? Well, we can just iterate over all robots that go from left to the right, and let's just sort all of them by the yi. And basically, just using a greedy algorithm, we'll just push the leftmost ball as right as possible. So how that would look? So the first ball would push, the first robot would push it here, then the next one would push it here, and so on. So there will be some rightmost position that we can push the leftmost ball. We can also do the same for the rightmost ball. At the end, if we have the positions L prime and R prime, then if R prime minus L prime is smaller than M, then we actually achieve our goal. This means that all of the balls will be next to each other. So that's the condition for us. We need to be able to push the leftmost ball and the rightmost ball such that the distance between them will be smaller than M. Okay. That's a solution if we have the directions. So what we can do now if we don't have those directions? So we can do some dynamic programming, but we need to be careful to not count any ways twice or skip any way of assigning directions. So let's say that we assign directions in such a way that the leftmost ball can be put to this position. That's as far as it can go. So that's as far as L can go with our assigned directions. Okay. This means that we had some sequence that pushed it from some initial position to this position. Okay. And so if we sort all of the ranges that we have by the yi, we can actually do a dynamic programming with the state of like position. So how many of the ranges that we processed, and well, let's say that this is count. So how many did we process, and the position of the leftmost ball after this. So this is the rightmost position that we can achieve. So we'll basically do our greedy algorithm inside of the dynamic programming. Yeah, and an important thing for us here is that we cannot be able, we shouldn't be able to put this ball anywhere to the right of the position that we fixed, because otherwise we would count some cases twice. Yeah, so this can be done with dynamic programming if we assume all of the ranges that end before this position. Then there are some ranges, the initial ranges, that might go through this position. So like this. There can be any number of those. Obviously, we cannot assign a direction for those from the left to the right, because then that would mean that we can actually push our leftmost ball farther to the right. So all of those need to have direction to the left. So we know that. Now, what do we have left here are all the ranges that start after this fixed position. So all of those ranges. What we can do here is we can do exactly the same dynamic programming as we did here, but with just sorting all the ranges by the left side, from right to left. And we need to be, yeah, well, we would again just fix some position, which is the leftmost position that we can put the rightmost ball. So R. Well, let's say that it looks like this, and the initial position was here. So there is some sequence that can put our ball here, and that's the leftmost position that we can go. So now, what do we need to have to be able to achieve our goal of putting all the balls together? We need to have, well, if the distance between those two is already smaller than n, then that's it for us. We just achieve our goal. If it's larger, then we can actually see that we have some ranges that go through the leftmost position, which can actually help us. how can they help us? Well, if they pass through this leftmost position of the rightmost ball, they can actually put, well, basically put our ball to the left of the leftmost one, which is definitely a solution for us. This way, we can definitely put all the balls in a row. So if there is such range that goes through both of those, then we have a solution. Or if the distance between them is smaller than m, then we have a solution as well. So just two of those cases. So the bottom line is that you need to fix this position and also this position, which is how far you can put the ball using all of the ranges from this side and from this side. Separately, you can do pretty much the same dynamic programming from both sides. And you need to handle the case of the ranges that go through this left position. That's it. Any questions? And I think that's it for the analysis.
Okay, so we will now do the scoreboard. We'll show the final results live. So let's set up the screen for this, and we will connect the projector. Możemy do waszego komputera to na samą drogę dostałem bez można nie ma coś tam?
Я перехідник на кафедрі.
Я перехідник на кафедрі.
Куди і був почти. Запис чи
Зупиніть, напевно. Можна написати там, що зараз за 2 хвилини продовжуємо.